All right, so today we're diving deep into a paradox. A paradox that, well, almost completely flipped the world of mathematics on its head.
Yeah, it's amazing, isn't it, how something that seems so basic could cause such a huge commotion.
Yeah, and we're talking about sets here. You know, those collections of things we use all the time, everyday things.
Exactly, and how just a simple idea about them could have led to, a meltdown in mathematics.
Total meltdown.
Yeah.
So where do we even begin with a story like this?
Well, I think it all starts with George Cantor back in the 1870s.
Okay, so we're going way back.
He was trying to to build a super solid foundation for mathematics for all of it, and he was using set theory.
So he was like the architect of math, trying to build this massive skyscraper, and sets were like his building blocks.
Perfect analogy.
Yeah.
And just like any architect, he needed to be super precise about the materials he was working with.
Right, makes sense. You can't build a skyscraper on, vague ideas and shaky foundations.
Yeah. Exactly. Defining sets in everyday language is easy, sure, but in math, you need a much more rigorous approach.
So how did he try to come up with this really precise definition?
Well, he started with something called axioms.
Axioms.
Axioms, yeah. Think of them like the ground rules, the fundamental truth that you just accept as a starting point.
Okay, so kind of like blueprints, the guide for how to put those building blocks, those sets together in the right way.
Yeah, perfect. And one of the most important axioms in early set theory was the axiom of comprehension.
Axiom of comprehension. Okay,
Right.
what does that one say?
Well, imagine you have a property, any describable characteristic. This axiom says you can use that property to create a set containing all the things that share it.
So like a set of all the people listening to this deep dive right now.
Exactly. In fact, the video we're using as our source today, it's from this YouTube channel called Scientia Todo Dia, and they use some really great examples, like a set of all yellow objects, or all numbers larger than 1,000, to illustrate this.
Yeah, those are good examples, really clear.
Right.
It seems pretty straightforward so far. I mean, where's the paradox in all this? Where's the catch?
Well, the paradox, it emerges when you start thinking about sets that can refer to themselves.
Wait, sets referring to themselves.
No.
That's where things get a little weird, right?
Oh, it definitely gets weird. And this is where we introduce two more brilliant minds, Bertrand Russell and Gottlob Frege.
More mathematician.
They were mathematicians. They were also working on the foundation of mathematics right around the turn of the 20th century.
Okay.
Now, Frege, he was developing this system. He called it logicism. And his goal was to show that all of arithmetic, all of it, could be derived from logic, pure logic, and set theory.
Wow. So they were going for like the ultimate mathematical unified theory.
Exactly. But that's where Russell's paradox comes crashing in. He came up with this thought experiment that, well, it kind of blew up Frege's project and really shook the foundation of set theory.
Okay, I'm intrigued. Lay it on me. What was this thought experiment?
Okay, imagine this, a set that contains all sets that do not contain themselves.
All sets that don't contain themselves? So, okay, I'm trying to picture that.
And that's where the paradox is, you see, because now the question is, does this set, let's call it R, does set R contain itself?
So if it does contain itself, then then it shouldn't, right? Because the rule is it's only supposed to include sets that don't contain themselves.
You got it. But on the other hand, if set R doesn't contain itself, well, then by definition, it must be included in the set.
So it's a catch-22. It's like this set is playing hide and seek with its own existence. It's like, now you see me, now you don't.
That's a great way to put it. And this seemingly simple paradox had some huge, huge implications.
Yeah, I can imagine if set theory, which is supposed to be the bedrock of math, if it could be messed up by this kind of contradiction, what did it say about math in general? I mean, was it all just built on shaky ground?
That was the big question, and it's a question we'll continue to explore in part 2 of this deep dive.
All right, listeners, hang tight. We'll be right back to tackle that question and delve into how mathematicians tried to fix this crack in the foundation of math. So we left off with this massive cliffhanger, this idea that the foundation of math could be, well, kind of flawed.
Yeah, it was a pretty big deal, a real crisis in mathematics.
A crisis. And all because of this sneaky little paradox about sets.
Right, it's like mathematicians thought they had this perfect system, this beautiful, elegant structure built on set theory, and then Russell's paradox comes along and exposes this this fundamental weakness.
Like a crack in the foundation, right?
Exactly. And it's not like you could just ignore it. I mean, this was about the very building blocks of math.
So what did they do? I mean, did they just abandon set theory altogether?
Well, some mathematicians, they did start to question the whole foundation, but others, they were determined to find a fix, to patch up this crack.
But how do you even start to fix something like that? I mean, we're not talking about, a leaky faucet here. This is about the fundamental rules of logic and sets.
It was a huge challenge. They had to go back to the very axioms of set theory, those ground rules we talked about.
Rewriting the blueprints.
Exactly. And they had to find a way to change the rules, to make them, Russell paradox proof.
Without destroying the whole system, right?
Yeah, it was a delicate balancing act. And one of the most successful solutions, I mean, the one that's widely accepted today, is called Zermelo-Fraenkel set theory. We usually just call it ZF for short.
ZF. Okay, so that was like the updated, improved version of set theory.
Yeah, you could say that it's basically a set of revised axioms that were designed to avoid those self-referential paradoxes that Russell pointed out.
So how does it actually work? I mean, how do you prevent these paradoxical sets from popping up?
Well, one way ZF does it is by introducing this kind of hierarchy of sets. It prevents sets from being members of themselves. It kind of breaks that self-referential loop.
So it's like setting some ground rules for the set family, No sets can be their own parents or their own children.
Yeah, I like that. That's a good way to think about it. By setting these clear boundaries, ZF manages to sidestep that whole Russell's paradox trap.
Okay, so, crisis averted. Math is safe again.
Well, not so fast. I mean, ZF, it's one solution, but it's not the only one. There are other axiomatic systems out there, each with its own, advantages and disadvantages.
So even with these new paradox-proof blueprints, there's still some debate about, the best way to build that mathematical cathedral.
Exactly, and it raises a really interesting question. Even if we accept ZF set theory as our foundation, does that mean we've achieved absolute certainty in mathematics? Is there anything else out there lurking in the shadows that could shake things up again?
Ooh, good question. I mean, are there other paradoxes out there, other cracks waiting to be discovered?
Well, that's a question that leads us to another brilliant mind, a mathematician named Kurt Gödel and his famous incompleteness theorems.
Okay, I think I've heard of Gödel. Didn't he have something to say about the limits of what we can actually know in math?
You're exactly right, and it's amazing how his work builds upon the questions raised by Russell's paradox. They both point to these inherent limitations in formal systems, even in a field as seemingly precise as math.
Okay, now you've really got me hooked, it sounds like. Like Gödel's work opened up a whole new can of worms. I mean, what exactly did he discover, and how did it change our understanding of logic and proof?
Well, that's where we'll pick up in part 3 of our deep dive. We'll delve into Gödel's mind-bending theorems and what they tell us about the boundaries of mathematical knowledge.
Okay, so Gödel incompleteness theorems. Those are some pretty big, pretty intimidating concepts.
They are, but they're incredibly fascinating, They really make you think about the nature of truth and what we can actually know.
Yeah, I mean, last time we were talking about how Gödel's work kind of builds on the whole Russell's paradox situation, the idea that there might be some limits to what we can do with math.
Exactly. Remember that analogy with the mathematical cathedral?
Yeah, the one where Russell found that crack in the foundation.
Right, and then ZF set theory came along, offered a way to, to patch things up.
But then Gödel's like, wait a minute, even with the best blueprints, there are still some limits.
Yeah, he basically said, even if you fix the crack, the blueprint itself, it still has some inherent limitations.
So it's like saying, okay, even with the best materials, the best tools, there are just some structures you can't build no matter what.
It's a great way to put it because Gödel, he showed that any system of axioms, any system that's complex enough, like the systems we use in math, they'll always have statements that are true, but that you can't actually prove within that system.
Wait, so you're saying there are like mathematical truths out there that we can never actually prove? How is that even possible?
It's a bit mind-blowing, but it's kind of like, imagine you have a map, right? And the map, it shows you that there's buried treasure on this island, but it doesn't give you the exact location.
Oh, I see. So the treasure's there, but the map just doesn't have enough information to actually pinpoint it.
Exactly. You can't use the map alone to find it.
So are these unprovable truths just kind of scattered randomly throughout math? Or is there some kind of like pattern to them?
That's a great question, and it's one that mathematicians are still trying to figure out.
Still working on it.
Yeah, but what Gödel showed us is that these limitations, they're not like accidents, they're not mistakes. They're built into the very fabric of formal systems.
So it's not about finding, like a better set of axioms or a more clever proof. It's a fundamental limit.
Exactly, and I think, at first you might think this is like a really depressing idea, right? Like, oh, we can never really know everything.
Yeah, kind of a bummer.
But actually, a lot of mathematicians, they saw Gödel's work as kind of liberating,
Liberating.
Yeah, because it freed them from this idea that they had to strive for this impossible ideal of perfect completeness.
So instead of being like devastated, they were kind of inspired.
I think so. It kind of shifted the focus, from trying to build this perfect system to understanding the inherent limits and then, working creatively within those limits.
So it's like, okay, we may not be able to know everything, but there's still so much to explore, so much to discover.
Yeah. Exactly. And it's important to remember, even though, absolute completeness is off the table, it doesn't mean math is broken,
Right. It's still working.
It's still working. We still rely on logic, on proof to build our understanding of the world. And those tools, they're still incredibly powerful.
Yeah. I mean, we're still using math to do amazing things.
Yeah.
Like sending rockets into space and building computers and all sorts of cool stuff.
Exactly. So it's not about, throwing out math or giving up. It's about, recognizing the limits and then seeing what amazing things we can do even within those limits.
That's a really great way to put it. So I guess the takeaway here is that even in something as seemingly perfect as math, there are still mysteries. There are still things we don't know and maybe we never will.
Yeah, and that's okay. That's part of what makes it so fascinating, right? The journey of discovery, it's just as important as the destination. And the questions that we can't answer, well, they're often the most interesting ones.
I love that the questions we can't answer, they're the ones that keep us thinking, keep us pushing forward.
Exactly. So to all our listeners out there, the next time you hit a wall, you come up against a paradox or a problem that just seems impossible, don't get discouraged.
Yeah, don't give up.
Embrace the mystery, keep asking questions, and remember that the pursuit of knowledge, well, it's a journey without a final destination, and that's okay.
That's a beautiful way to end this deep dive. Thanks so much for taking us on this incredible journey through the world of paradoxes and the limits of logic. It's been a real mind bender.
My pleasure. It's always fun to explore these big ideas and to see how they connect to our everyday lives.
Absolutely. And to all our listeners, thanks for joining us. We'll see you next time for another deep dive into, well, who knows what fascinating topic.